This video deals with the shift of position of the pivot point while handling ships. We will see that existing theory, although simple to remember and handy to work with, fails to explain a few limit cases. I will try to demonstrate that other basic physical principles explain better the movement of the pivot point along the ship's axis in various situations. It will also promote the idea that evaluating the effect that a sideways force has on the rotation and on the lateral movement of the ship is more practical at all stages of ship handling than strictly dealing with the pivot point. Let's start with well-known situations. Our small-scale model will turn around an open dock. When a third of the ship will be clear of the corner, the ship will kick ahead on a hard-to-port wheel. As we have all learned, the ship clears the dock since the pivot point is about 1/3 from the bow when moving ahead. Here is another example. In the next situation, the ship is moving astern. Since my homemade model was too basic to be fitted with a bow thruster, I simply use a string to give an efficient side thrust as necessary. The pull is given when a third of the vessel is clear of the dock. So far, so good. The classic pivot point theory does perfectly well. Now watch our ship going astern and having a very effective stern kick to port. A third of the ship clears the dock, kick, ouch. Now going ahead and having a very efficient bow thruster action. Once again, it's not going as per plan. Let's try a different type of efficient underwater thruster. Where is the pivot point? It is lying at about 75% of the ship's length, so 1/4 ship's length from aft. From the last three examples, we can see that the classic pivot point theory has its limitations. I will try now to introduce a different approach of the pivot point. But before we do, let me show you the detail of my highly sophisticated homemade bow thruster. Of course, in most of our rivers, it would not be very practical. When you apply a side force on a ship, anywhere along its length, it does not only cause the ship to rotate, it also makes it move sideways. Therefore, it cannot be compared to a body with a hole in its axis through which a spindle is passing. A ship is not pivoting around a fixed axis. Let's start by making a clear distinction between the center of lateral resistance and the apparent pivot point. The center of lateral resistance of a vessel is that point where, if you apply an effective lateral force, no rotation, if the vessel has a steady heading, will occur. Acting on this point, a lateral force has no arm lever, therefore no turning moment. It only pushes the vessel sideways. A force acting ahead of the center of lateral resistance will rotate the ship in a different direction than the same force acting astern of the center of lateral resistance. The lateral resistance can also be called hydraulic lift. The position of the center of lateral resistance is function of the center of the underwater surface area, the center of gravity, and the fields of pressure around the hull. The starting point of the center of lateral resistance is the center of underwater surface area, which is normally close to the center of gravity of the ship. The position of the center of the underwater surface for one ship is mainly affected by the trim. A trim by the stern moves the center of lateral resistance point more aft. A trim by the head moves it more forward. We can see that the apparent pivot point of a ship trimmed by the head with headway is more forward, and the apparent pivot point of a ship trimmed by the stern with headway is more aft. The field of pressure, bow wave, and the stern sub pressure under headway shifts the center of lateral resistance towards the area of higher pressure. This is mainly due to the positive pressure built around the bow in the forward motion, which creates a more resistant surface for the hull to lean on when pushed sideways. For practical ship handling purposes, it seems that the shift of the center of lateral resistance due to the speed is rarely more than 10% of the ship's length in the direction of the ship's movement. The apparent pivot point only exists when the ship is rotating. The position of the apparent pivot point at a given moment depends on the hull underwater resistance to lateral movement and the efficient lateral forces applied on the vessel. In order to estimate the position of the apparent pivot point, we must assess how a lateral force will affect the rotation of the vessel, the sideways movement of the vessel. Let's suppose that you have a bar-shaped body at rest in space and you apply a lateral force on it at one end. The resulting motion can be decomposed in two parts. First, a sideways bodily motion. Secondly, a moment of rotation about the center of gravity. These two results, when combined, will cause a change of position of the body after the force has been applied for a period of time. We realize that the part of the bar that has not changed position in space, P, pivoting point, is not located at the center of gravity but some distance off it, away from the end on which a force is applied. The position of the acting lateral force. A lateral force acting away from the center of lateral resistance will, for the same angle of rotation, push the center of lateral resistance relatively less sideways than a force acting closer to the center of lateral resistance. This results in an apparent pivot point further at the opposite end of the vessel. The closer to the center of lateral resistance the force is acting, the further away to the opposite end the apparent pivot point will be. This can even result in a pivot point outside of the vessel's physical limits. Lateral resistance. As we have seen earlier, the lift is the resistance of the water to any lateral movement of the vessel. The hydraulic lift varies with the shape of the hull. A more profiled, narrow hull will induce more lift. Let's compare two ships with the same length, same draft, the first having only the third of the beam of the second one. After the ships have developed sideways motion, it is harder to stop the drift of the wider ship, 3 times heavier for approximately the same lateral resisting force. That resisting force being here the surface area of the wall of water, which is represented by the ship's length times the draft.